Welcome back, students. My name is Dolon Banerjee and we are continuing with the video lecture series conducted by AKTU on Geotechnical Engineering, which is a part of Civil Engineering course. So, in the last class we were discussing about the consolidation process, and now we will discuss about how this settlement or consolidation settlement is measured. Okay, so we will go through different formulas. So, let us begin. So, today we will be discussing about the formula to determine the compression or consolidation of the soil. Okay, the settlement is the another name for the consolidation only. The basic concept: the compressibility of soil is expressed in the terms of a plot between the void ratio on y axis and effective stress on the x axis. So, what does this mean? In generalized term, we can say that E will be here and effective stress sigma bar. Okay, this is the effective stress. This is the effective stress. So, this is the sigma bar. The plot is made between these two in order to find out the settlement. So, we will see how these are find out or calculated later on. Void ratio is used to represent the compression because it is a ratio of volume of voids to volume of solids, the former being reflective of the compression and the latter being constant in the compression, soil compression. Okay. Actually, what does this mean? If you remember in the previous classes, I told you that E, which is the void ratio, is actually given by V V upon V S, where V V is the volume of voids, okay, upon volume of soil solids. Okay. So, volume of voids upon volume of soil solid, this is the ratio, that is E. Now, if you see, if we are given a particular amount of soil, say 1 kg, then in whichever way we disperse it or arrange it, the volume of voids only will be changing in this. Okay. The mass of soil solids or the solids amount and its mass will obviously remain constant in this 1 kg of soil, or we can say that this particle concentration will be constant in this 1 kg of soil for that measurement, we can say. Okay. So, this much, or if you say this is the V s, okay, then this is constant, this will be constant for a given constant measurement of mass. Talking about V V, if this we take as a V V will be comprising of water and air, both of them. Okay. So, the case may vary that if it is loosely packed, then volume of air may increase. If the water is there fully saturated or partially saturated, then V W also may vary, but this will remain constant. Okay. So, we can say that E is a very good measure because it is V V upon V s. Here this is constant. Okay. This is constant and this varies according to the compression. Okay, compression, or we can say that consolidation. Which has taken place into the soil. Okay. Due to this parameter and this parameter may vary, hence this will vary. So, this statement is saying that only that this E is used in order to find out the consolidation or we can say compression. Why? Because this is a constant parameter and this only will vary because of the compression. So, this will rather give us a better indication of how much compression or how much consolidation has taken place. Okay. the construction of any structure takes place in stages causing stresses in the soil also in stages. Means what is it saying? That we know that when a building is to be made, okay, in the ground, a building is to be made, suppose, then first of all what is done? First of all, excavation will be done for the foundation. So, we can show excavation something like this. Okay. This is the excavation. Excavation has been made here. Now, what will happen? The foundation or the footings will be designed and they will be made or constructed, something like this. Okay. Something like this, footing will be made. Okay. If it is a raft footing, then we can say something like this will be made. Then again the soil will be filled in all these parts. Okay. Again the soil will be filled up to this level, then only the substructure and all other parts of the structure will be made. Okay. So, what does this mean? This means that if we talk about the soil lying here, if we are concerned with this soil which is lying underneath this construction part somewhere here, then we can see that how will it undergo different changes. If we consider this first stage, it was having the general condition something like this. Okay. It was having this much of, what was this? This was the overburden pressure, overburden pressure. Okay. And once this soil or this part of the soil was removed in order to have an excavation, what happened? We got something like this and the soil, this was already here. So, now what happened? The stress release was there. You can understand this, that the overburden pressure is released because the soil is removed. So, we can write this as no overburden pressure. Okay. Now, further we will be constructing the foundation. Okay. We will be constructing the foundation. So, something like this, a footing will be there. Okay. Footing will be constructed and later on the whole structure will be there. We can say like this, if the soil is here, the footing will be here and whole structure will be there, something like this. Okay. So, you can see the construction is done in stages. First of all, there was normal ground, then an excavation, then a footing, then the whole structure. So, the stress is also varying. Here was some stress, then it was free, again stress of foundation was there, then the whole structure was there along with the footing and the soil. Okay. So, we say that the construction of any structure takes place in stages, causing stresses in the soil also in increments of stages, okay, by this procedure. So, then the to represent this field condition, the laboratory consolidation test is conducted by applying stress in increments on an undisturbed soil sample, allowing sufficient time for the complete consolidation to take place under each stress increment. What does this mean? You have already seen how the process works in the ground or on the field. Okay. In the laboratory, what we will be doing? In order to simulate or in order to get the same simulations as in case of the ground. So, what we will do? We will first of all take a stress or increment a definite stress on that soil. After that, we will wait and let it get into consolidated process until it is fully consolidated or settled for that stress. After that, another increment of the stress will be done, so that we will be able to counter or we will be able to count how much settlement now due to this increment will be taking place in that soil specimen. Okay. So, one by one we will be carrying out this process. So, if say there is a specimen of soil something like this, okay, something like this. First of all, we will stress it out or apply a load of say 1 kilonewton, then find out the total consolidation settlement. Then again leave it. Okay. When once total consolidation settlement corresponding to this load is found, then we again increase the load on the specimen. Now, we will be having a load, let us say 4 kilonewton, okay. And again the process we will be doing total settlement, okay. Again then further we will increase the load if we are required to do so, okay. A typical laboratory consolidation test consists of loading an undisturbed soil specimen with a given stress increment and recording the vertical compression of the specimen with a dial gauge at regular time interval for sufficient time. The same thing is again told here, that we will be applying a dial gauge here somewhere. Suppose you can keep a dial gauge here only, something like this, okay. This is the dial gauge, it will have markings. This will be here. So, it will see that how much settlement is going to happen, okay, in due course of time. We will leave it, once the load is applied, we will leave it for a sufficient amount of time, maybe for 2 days, 1 day, or whatever may be the case, depending upon the soil as well, okay. So, we will leave it for a large amount of time, and at regular interval of time we will take the dial gauge reading, that how much settlement has taken place. Then continue with a increment of the stress afterwards only when this dial gauge shows no further settlement, okay. When the settlement ceases in this specimen, this will show no further settlement, then only we will increase the stress further, and again we will go into different times to find out the settlement. The next stress increment is applied only after the compression of the soil is completed under the previous stress increment and the process is repeated. As I just now told you, that next stress increment will be applied only when this dial gauge shows that no further settlement is taking place, okay. Representation of laboratory test results. There are the following two types of results that are obtained from the laboratory consolidation test. One is the E and sigma, okay, sigma bar result, means E, just now I told you or showed you also this graph. One is this graph, okay, and what is the another graph? That is the dial gauge, okay, dial gauge reading, or we can say the settlement and time graph, okay. We can also say this is in mm, this is also can be told as settlement and time graph, okay. Two mainly these two graphs are used to represent or to locate the results of the consolidation test. Compression of a soil as a function of effective stress increment expressed as a relation between the final void ratio, also known as equilibrium void ratio, on the y axis versus effective stress on the x axis, as shown in the figure, okay. The figure you can see, this is the figure, okay. These are the figure. The figure 1 shows us E versus sigma bar, and figure 2 shows us E versus log sigma bar, okay. This is base 10. So, in this you can see, when we are using the only effective stress, then we find a curve, okay, while when we use the log sigma bar, then a straight line is obtained. You can see that this is the difference between the log graph and general normal graph, okay. Void ratio is the same here, only we have changed the log table and general, then we find the curve and straight line, okay. So, this is the representation of what we get in the consolidation test, because in consolidation test we find out E, okay, suppose E1 and E2, and corresponding to this we find sigma 1 bar and sigma 2 bar, means how much stress. Suppose one stress of sigma 1 is applied, then what will be the corresponding void ratio? Again sigma 2 is applied, then what will be the corresponding void ratio? And finding out this, we will be plotting the graph, okay. Compression of soil as a function of time at a given stress increment expressed as the compression delta H or dial gauge reading on the y axis and time. As I have already told you, the graph will be also made between the settlement, you can say, or dial gauge, you can say, dial gauge, okay, and here will be the time, something like this graph you can see here. So, this is the dial gauge reading in mm, okay, and this is the time in minutes. You can see it is also bifurcated in 3 different parts: initial compression, primary consolidation, and secondary consolidation. If you remember, in the last class we discussed about the initial, primary, and secondary consolidation. So, initial compression is already here, has been happened here, and which we are not considering for this part, because we are mainly concerned with primary consolidation and secondary. In these also we are mainly concerned with the primary consolidation only. Okay. So, leaving apart the initial compression, we will just see we can see that this is the graph which is obtained, and here this is u is equals to 0. If you remember, what was u? What was u? It was degree of consolidation. Consolidation. Okay, this was the degree of consolidation, which tells us about the percentage of settlement that has taken place. That has taken place. Okay. Percentage of the settlement that has taken place. So, in this case, when this is the initial point, then obviously u will be 0. Okay. And here you can see this is u is 100%, means the primary consolidation is over here, it is done. This much is the primary consolidation only. Okay. Or in between the it will vary. Okay. In between this is just 50%, u is equals to 50% is here. Okay. Likewise, the things will vary, and this is the secondary consolidation, which was, if you remember, this was due to the reformation of soil particles. You can say reformation or rearrangement also. Rearrangement as well. Okay. Okay, this is clear. Now, numerical, what outcomes means, from those graphs what are the parameters which we can derive. Okay. So, we will be talking now one by one about them only. Figure shows a typical void ratio and pressure relation obtained from the laboratory consolidation test. When both void ratio and pressure are plotted on an arithmetic scale, the following 2 important parameters or terms are obtained from this curve. Okay. So, coefficient of compressibility, this is one, this is represented by A V. Okay. This coefficient of compressibility is the slope of the void ratio pressure curve when both are plotted on the arithmetic scale. What does this mean? No, this one, let me clear it out. This is the curve, okay, and the slope of this curve, slope of this simple arithmetic, means E and sigma bar curve, gives A V. Okay. So, we can say that this will give you this and this will give you what? The A V. What does the formula then become? If you just find out, because it is a slope, then slope will be equal to delta E upon delta sigma bar. Okay. Just a negative sign is put here in order to make you understand that with the increase in the stress or effective stress, this will decrease. Okay. Hence, it is made a negative sign there. You can see here. Yeah, this is the negative sign and this is the formula, delta E upon delta sigma bar. Thus, the coefficient of compressibility is defined as the ratio of change in the void ratio to the change in effective stress. Just now I told you. Okay. The negative sign is used to indicate that void ratio decreases with the increase in the effective stress. I am sorry. Okay. This is the point. because in the diagram or in the graph also, if you see, you can see that with the increase in the effective stress, the void ratio continuously decreases. It is continuously decreasing as we increase the effective stress. Okay, you can see here like this, as it is increasing, this is decreasing, hence a negative point sign is made there. Okay, to understand this phenomena only. The next one is coefficient of volume compressibility. Okay, MV, coefficient of volume compressibility. The coefficient of volume compressibility MV is defined as the ratio of change in the volume of soil to the change in the effective stress per unit original volume. Okay, what does this mean? MV, by definition, if we move change in the volume of the soil, okay, to the change in effective stress per unit original volume, means upon, you can say, change in the effective stress per unit original volume V. Okay, you can say something like this, or you can also write it as delta V upon delta sigma bar into 1 by V. Okay, you can write it like this also. So, what is V1 here? V1 is the original volume. Figure shows the three phase diagram of the soil. Here Vs is the volume of the soil solids, Vv is the volume of voids, and the volume of air is Va, which is 0 here, because theory of consolidation is applicable only for the fully saturated soils. Let us see. Okay, this is the diagram, phase diagram. Okay, here this will be the phase diagram. Here you can see this is only water, and here is only soil solid, no air. Va is 0. Why? Because consolidation process is only valid for fully saturated soil. Fully saturated soil. Okay. So, this is the one. Now, you can see if this is the void ratio, you already know the formula. Considering unit weight of the soil solid Vs being 1, what will we have? What will we get? E is equals to Vv by 1. So, this becomes Vv only. Okay. So, E gets equal to the Vv. Now, initial volume of the soil was V1. Just now we told, okay, we talked about this, that this is the initial volume or original volume. Okay. So, V1. So, what will be V1? V1 will be equal to, as now you know that Vs plus Vv. Okay. What is Vv? It is E, and what is Vs? It is 1. So, V1 will be equal to E plus 1. Okay. This is what written here. Then further, it is only the derivation of that same. Okay. Because just now we had defined it that delta V upon V1 into 1 upon sigma bar. Okay. No need to write this one. No need to write this one. Okay. This will be the formula for MV. Okay. This was the formula for MV. So, we are slowly deriving it to get that relation, that delta V upon V1 is also equal to delta H upon H1. Okay. This is also a formula. Okay, we can find it. You can just see it. Just now what we got, V1 equal to this. Okay. So, we just derive the formula that this is equal to V1 minus V2 upon V1. Okay. Again A and H1. What is this A? A is the area of cross section. Okay. H1 and H2 are the heights. Okay. What of the specimen? What is A? Here A is the area of cross section of specimen. Okay. And what is H? H1. H1 will be the initial height. Initial height of specimen. Okay. And what about H2? Let me write here. Obviously, final height of specimen, which means after the consolidation or after settlement, we can say. So, it will be lesser obviously. Okay. So, just they have derived to be equal to this, hence we find that delta V is equals to H2 H1 minus H2 upon H1, that is delta H upon H1. Okay. So, now what we have? We have this, that delta V upon V1 is equal to delta H upon H1, which is equal to delta E upon 1 plus E1. Okay. Now, we have this formula with us, this whole formula with us. Further, we also know that mv was delta V upon V1 into 1 upon delta sigma. So, this part can be now replaced by this as well as this. Okay. So, one formula what we will be now obtained, delta H upon H1 into 1 upon delta sigma, or one another formula will be delta E upon 1 plus E1 into 1 upon sigma. Okay. Now, just now if you remember, delta E upon delta sigma we just now read as AV. Okay. So, this can be written as AV upon 1 plus E1, and but this was also with negative sign. If you want, you can also write it minus AV upon 1 plus E1. Okay. So, now if we sum up, so let me sum up. MV has a formula delta V upon V1 into 1 upon delta sigma. Okay. Or it has a formula delta E upon 1 plus E1 into 1 upon delta sigma, or it also has a formula delta H upon H1, which is into 1 upon delta sigma, and another formula will be del mv is equals to AV upon 1 plus E1. Okay. So, these many formulas are there for mv. What is mv? Volume compressibility, coefficient of volume compressibility. Okay. Because we are treating the whole expression with the volume change only due to the effective stress change. Now, compression index. What is compression index? If you remember AV, what was AV? It was for this graph. Yes, for this curved graph AV was calculated. Now, what is CC or coefficient of compression? This is for this graph, the log one. For this will be straight line. This is a curved line. You can see that the slope here is different from the slope here. Okay, clear. The slope here, okay, this slope and this slope here are different. You can see it. Okay, so this is less reliable. AV will be less reliable. So, generally we use this one only, which is CC, because CC is the slope for this line, and this is a straight line and it has a constant slope anywhere throughout the whole curve or whole straight line. Okay. So, we will generally use this one only. So, let us see what is CC now. Compression index CC. The second figure just I showed you shows the more commonly used void ratio pressure relationship, where the effective stress is plotted on a log scale as the E log sigma bar. Relationship is observed to be linear for typically normally consolidated clays. That was that diagram which was there. Let me make it here only, log sigma and E, something like this. This is mainly for normally consolidated clay only. Okay. And this will give you the CC, coefficient of compression. Compression index is the slope of this plot and is defined as the ratio of change in void ratio to the corresponding change in the effective stress. It is defined mathematically as this. So, just if we write what will it be? Delta E upon what will be this? Delta of log sigma bar, and this can be again refined and written as C c can be written as delta E upon log of, if let us say this is E 1 and E 2. So, corresponding this will be sigma, let us say this is then sigma 1 and this will be sigma 2. Okay. E 1 corresponding sigma 1, E 2 corresponding sigma 2. Then the delta E will be E 2 minus E 1. Okay. E 2 minus E 1 will be delta E. Then what will be log? Means delta, what will be about log? It will be sigma 1 by sigma 2. Okay. Sigma 1 by sigma 2. Why by? If you know that in log, if we write log sigma, what was it? It was sigma 1 only. So, we can write it log sigma 1 minus log sigma 2. Okay. Because we have to write this only, and this means we know the rule of log, it will change into log sigma 1 by sigma 2. Okay. So, I have directly written that only. So, this will be the formula for compression index, that is C c. Okay. We can write it like this also, or we can write it like this also, anything you can write, where E 1 is the void ratio at effective stress sigma 1 and E 2 is the void ratio at effective stress sigma 2. The negative sign is used to indicate that the void ratio decreases with the increase in the effective stress to make it compression index positive. You have seen that this is negative here. So, due to this negative only you can see that this is sigma 2 first and then sigma 1. I have written in positive form. So, sigma 1 is before and this is later on. Okay. The same this is the same expression, just you have put in a negative sign here. Okay. Further, different other formulas also can be found out. You can see that the same is solved here, sigma 2 by sigma 1 is made here. Okay. This is the same formula which is being derived here. Okay. Main we have the formula this only. Okay. You have to remember this formula, where delta E is the decrease in the void ratio when the effective stress increases from sigma 1 to sigma 2. The compression index is usually determined for E log curve obtained from a laboratory consolidation test. In the absence of consolidation test data, compression index may be computed from Skempton's equation. Okay. We have two equations given, you can see, for undisturbed clay and for remolded clay. Sometimes in the numerical we may also be not given the value of C c, that is delta E not given, or maybe sigma 1 by sigma 2 value may not be given. Then in that case we can use this formula. Okay. This consists of, this is the W L which is the liquid limit, this is the liquid limit. One is the 0.009 W L minus 10 and one is 0.007 W L minus 10. Okay. For obviously C c will be more for undisturbed. So, this is 0.009 and for remolded it will decrease. So, it is 0.007. Okay. And the rest formula is same. W L is the liquid limit of the soil specimen. The properties of AV, MV and CC are useful to determine the ultimate consolidation settlement of the soil under any circumstances. I am sorry, under any circumstances effective stress increment. Okay. We will go into the settlement formulas also in the next classes. For the time being, you have to understand that this MV, AV and CC will be used to find out the settlement. Okay. So, these are the formula when C c is not given to us or any of the parameters are missing in that part. Okay. In that case, we can write this or this 0.009 and 0.007. Okay. So, some related questions are asked here, please go through them, and next time we will again continue with the consolidation pressure of the soil. Okay. Thank you for connecting with us. Please keep watching the videos. On the next class we will again meet. Okay. Thank you.